Girish, Assistant Professor, Department of ECE, ATM College of Engineering, Mysuru. In this video tutorial, we are going to demonstrate making use of the internal PWM in order to generate a pulse width signal along with the status of a fading LED in the hardware kit. Okay, so here internal PWM play a vital role. Okay, so PWM pin is responsible for generating the waves is also necessary. Okay, so PWM along with the LED10. So here the LED pin which is output. So pin number 1.23 will be used for the showing the status of the PWM signal. Okay, of course we are going to making use of CRO in order to represent output value as well as the voltage value if you want to display. Okay, so now before going to that, actually the LPC1768 has 6 PWM blocks. Okay, totally it has 6 PWM blocks in which that can be used as 6 single edged or 3 double edged. Okay, so there are about 7 matching registers they are supporting for the PWM output signals. Okay, so now here in the program PWM1 block number 1 is used. There are multiple registers which is going to be used as IR, TCR. Okay, anyhow, once I move into program, I'll explain wherever I got the register along with its function. Okay, so now let me move to algorithms, how to configure the internal PWM which is being available at LPC1768. So configure the GPIO pins of PWM operation in the respective pin select register. Configure the TCR. So TCR is nothing but timer control register. Okay, to enable the counter for incrementing the TC to time count and enable the PWM block. Okay, and set the required prescalar value in PR. So PR is a prescalar register. We are going to specify the prescalar value. Okay, in our case, let us think that as a 0. Okay, so configure MCR. So MCR is a match control register which is going to be used to control the resetting of TC, that is a timer counter. Okay, and generating of interrupt whenever the match interrupt occurs. So whenever the match occurs, at that time the MCR is going to be match control register making use of to resetting the time counter. Okay, it matches with the MR0. Okay, so MR0 which is going to be a primary match register which holds the maximum duty cycle time. Okay, T on plus T off, or maximum cycle time. Sorry, fine. So then match registers will give you the values of duty cycle. Okay, so now load the duty cycle for the required PWM block channels in the respective match registers of the corresponding PWM. Okay, so if it is PWM1, then MR1, PWM2, MR2, like that, the respective match register will be responsible in order to load the duty cycle. Enable the bits in LER register. So where LER register is a load enable register, it will make use of enables use of a new PWM values once the match occurs. Once the match occurs, again load the enable register and enable the required PWM channel in PCR. So PCR is PWM control register which enables outputs and select the PWM channel types as either single edged or double edge control. Okay, so single edge and double edge configuration will be taught in the theory class. Okay, so here program for the internal PWM is very simple here. So hash include LPC17xx.h. It's going to be defined the definitions of LPC1768. So void PWM init. So PWM initialization block, and make sure it should be in small letter itself because this is the inbuilt function of PWM. Okay, and void PWM1 IRQ handler since is a NVIC nested vector interrupt control number. Okay, and unsigned long integer I and flag 1 are the intermediate variables used for to generate the PWM signal. Okay, so the main part of the program, system init, system core clock update are the main functions of clock and PL update features built-in function of CMSIS. Okay, now I'll call the PWM. Once you initialize the PWM, so very simple, I'll go to load with 0 and I'll go to compare with 1000. So increase your value and simultaneously depending upon the I value you should generate a PWM signal. That's the aim. Okay, so here PWM initialization, it includes peripheral enable through power. Okay, so by moving the particular value into pcomp register. Okay, pin control of peripheral. Okay, then pin select 3, so which is going to be cleared if any other functions are enabled. Okay, in the register. PLC again pin select 3 will be loaded with 80 because PWM 1.4 is selected for the P1 pin 1.23. So 1.23 is a LED pin, for that PWM 1.4 is selected. Okay, so here PWM 1 prescaler. So prescaler, as I said, is count PR value, prescaler value. Okay, so here prescaler register we are going to have is 0 in our case, as I said in earlier, which is going to be count the frequency from the processor clock. Okay, and PCR, as I said, PCR is a PWM control register which will going to enable you in the single edge or double edge operation. So which is going to be select, if you load this value into the PCR, then it will going to work in single edge. And MCR is, as I said, match control register. Okay, MCR is match control register which is used to control the resetting of the TC. Okay, so once you write 3, reset and interrupt on PWM MR0. So MR0 value will be resetted once the match has occurred, and MR0 value here is 30000, which is going to be a count for the match register. Okay, so MR4, which is going to be have 100, which is a maximum duty cycle count, which is going to be set for the MR1. Actually, you can making use of MR1 or MR4 here. Okay, anyhow both will come. And LER is, as I said, it's a shadow copy register. Okay, so LER is going to be load enable register in order to perform the new PWM values once you match. So TCR is a timer control register. It's used to control the timer counter function. Okay, so timer counter function, enable, disable, resetting the timer counter. Okay, so this is called 2 times in order to reset the value first and then in order to enable the PWM value with the R desired. Then we call, once you initialize the thing, you can call the NVIC IRQ number of PWM1. So once you call the IRQ number, which is going to check the flag status in the next slide, I'll show you. Okay, so here the IRQ handler, which is going to check the IR register, that is interrupt register of PWM. Okay, so what is actually it will going to do? This IR can read, identify which of the 8 possible interrupt sources are pending. Writing logic 1 will clear the corresponding interrupt. Okay, so if you are writing the 1 to the register, then it will going to clear the corresponding interrupt. So totally there are 8 possible interrupts with the source of IR. Okay, now if flag is 00, PWM is MR4, so 100% duty cycle. For 100% duty cycle, so we are going to load with the MR4 is 100. Then PWM 1 LER, so LER load enable register. So once you have match count equal to 100, then you should load the value into new value into LER. Okay, it will going to load the new values, PWM values, once the match occurs. So for that reason, we should move FF to the LER. Okay, LPC PWM1 MR4 now. So it will going to increase every time by 100 here. Okay, every time by 100, and then if it is reaches 2700 value. Okay, MR4 is 2700 value, and then again, so it means that flag needs to be set and LER should be set as FF. Okay, so that match occurs and then it is loaded with new value. Else decrement that by 100 and then once you match this count, MR4 value comes to 0, then again load the new value. Okay, so here once it reaches 0x500, okay, so 500 here, so we are going to take for so the duty cycle which is going to be visible. For that reason, MR4 is loaded with 0x500. Once the MR4 value reaches 500, again PWM1 block loaded with new value. So every time whenever the MR4 which is going to be reach the value of 27000 and 500, which is to show the duty cycle from 1% to 100%, the values are calculated here. Okay, and once we look out the registers of PWM in the manual, we will come to know why the particular value has been loaded. That will explain in detail in the further explanation videos. Okay, so here you can find the simple operation of register PWM block here. MR1, it will go to until it reaches comparator, will going to set the new state. If it is crosses 6, the same state will follow. Once it reaches 100, so it will going to send the new value. Okay, so this is what the way MR1 duty cycle shadow register 60%. Once 60% is reached, comparator value will set to new state. So once that new state count reaches to 100, again comparator will check the counter value. So if it is 100, again it will going to change the new state. Okay, so shadow registers are used to match the value of duty cycle values. One for MR0, that is for 100, another for on time what you need. Okay, so in our example we never like compare with the 60% or 40%. So what we are going to do is we are continuously generating the varied pulse width modulated signal. Okay, I'll show you how the signal will be and the indication of LED in the next slide. So you can observe at the LED10 in the experiment. Okay, so if your LED10 is intensity of the LED is varying, then you got the waveform of pulse width signal. Then you can cross check the connections in the CRO and you can observe the PWM signal which is shown here. Okay, so now we can have a demonstration video which is X files downloaded into hardware. Okay, so thank you. I hope you understood the program flow of internal PWM. Now let us demonstrate in the hardware. So now to download, you need to check whether your hardware is connected to your PC. So I hope you observe the device ID as we did in the previous examples. So now let us download the X file. So LPC to an ISP, that command along with the full path of your X file, that is int PWM, then say enter. Observe that the program is downloading into hardware. Now reset your code. Before resetting, make sure that the proper connection has been made. So the internal PWM pins are responsible with C and B connectors. So C and B. So here the LED10 is used to show the intensity variation of the pulse width signal. So that is PWM signal, that is LED10. So now in the PWM signal you can observe the two outputs, namely voltage and the pulse width signal. Okay, so now I'll connect the probe positive into output, that is TP5, and another end should to the ground. Okay, so now I'll check. So I'll reset my code now. Once you launch this code into hardware, you can observe that the width of the pulse is varying. So since it has been done with the program itself, no need to change the duty cycle and all. So we have like continuously changing the duty cycle. So for that reason, you can observe the width modulation of the pulse, and also observe if you want to observe the voltage level. So you can observe the voltage level too. Okay, so adjust your channel accordingly in order to observe the voltage level. Okay, so you can observe that voltages. So voltage level is varying. So the same variation is also showing in the LED 10. Okay, so you can observe that intensity of the LED is going to be fading. Okay, so fading of LED shows that you are getting the output. Okay, so the width variation of the pulse as well as the intensity variation. Okay, thank you.